I know that was you, so I'm going to look for it.
Okay, guys, welcome back. In this video, we've got a pretty cool section. I think you guys will like this part. We're going to talk about motion and frames of references. Motion and frames of references. You're supposed to write down what motion is in your guided notes. So if you're watching the video, please be following along with your guided notes. Write down the definition for motion. Right, like it says, motion is a change in position. So if you change your position, you are in motion. Okay? Change in position. I've got some pictures I just pulled off the internet of motion. You type in motion is what you get. How do you know that this bullet train here is in motion? Okay, good. We can compare, the train is in focus and everything else is kind of a blur, which kind of implies that it's moving, right? Okay. What about this guy on the bike? How do we know he's in motion? Same thing, but what else? From past experience, what would you know he has to be in motion?
He's pedaling.
How do you know that? It's a still frame.
He's not falling over.
He's not falling over. On a bike, don't you have to be moving in order to do that?
Yes.
Okay. So we could use past experience of riding a bike. But then also, there's things that are blurry in the picture. Okay, how do we know this inchworm here is moving? Or caterpillar. How do we know he's moving? Whatever he is, I don't care.
His body's bending because that's how he moves. Trevor.
Okay.
I guess that's the wrong answer.
We can tell from past experience they have to kind of like inch their way across and crawl that way. What about this comet? How do we know it's in motion? It's leaving a trail, right? So, okay, very good. We're going to talk about motion and how we know we're in motion today. It gets a little more complicated than just that. So, please be following along. Okay, like this slide says, an object is in motion if it changes position relative to a reference point. So an object is in motion if it changes position relative to a reference point. Well, okay, what's a reference point? What is a reference point? Well, here's a definition. A reference point are objects that are stationary. What does stationary mean, guys? Which means not moving. So stationary means not moving. Such as a tree or a sign or a building. These types of objects make good reference points. So, let's use an example. This guy on the train. Okay? He's looking out the window. What would be a good reference point for him? A tree, or a bush, or a rock, or something out here that's not moving, right?
Yes.
Then he could tell that he is moving. What if he looked over across the aisle at somebody and was talking to them? Just looking at that person next to him, would he be able to tell that he's moving? No, because they're moving relative to him. So motion is relative. Could you say that?
Yeah.
Motion is relative. Okay. I got this picture here. Okay, skydiver. Could this person look at this person and determine if he's moving?
Yeah.
No.
Yes.
The answer is no. Why?
Because he's moving to say.
When they're falling, you see clouds go up.
No. He's not looking at the clouds.
Freaking falling.
But he has peripheral vision.
No, he doesn't have any. He doesn't have any peripheral vision.
His goggles are blocking it.
He's tunnel vision, looking at his girlfriend over there. Is that girl? I don't know.
They're going to the movies.
So no, you're right. You're right. Just listen to my question again.
Okay.
If this person looked only at this person, could he tell he was in motion?
Yeah, they sound like
I
their
guess
hair
not.
moving.
His stomach's probably dropping.
No.
He can't. Because this person is moving at the same speed he
But
is.
what if his cheeks were flapping in the wind right
Yeah.
now? Tell him to speak that way.
Okay, he might be able to use other senses, like feeling, to tell. But I said if he was just looking at that other
No,
person.
he could just look and see.
Okay, maybe I should ask it this way. Would this person make a good reference point for this person?
Yes.
No.
No, because they're both falling.
They're both moving. They're both falling. What would make a good reference point for this guy?
Got cloud.
Okay, maybe the cloud.
Ground.
The ground. Maybe he's looking at the ground. Maybe he looks back up at the airplane that just dropped him off. Could then he tell he was in motion? Yes, that would make better reference points. Okay. But actually, the plane would be moving too, and the clouds would be moving too. So maybe the ground is the best reference point for this guy.
Well, I don't know how
Reference points are better when they are stationary, which means what?
Not moving.
Not moving. Okay. Maybe I shouldn't have put that slide in there, huh? Okay, probably
How
not.
do you
Maybe
not know you're
I'll
going
delete
if
it.
you jump out?
I'm gonna delete it.
You can use the Vegas and all these reference.
Jump out. plane.
Okay, here's a better one. Here's a better slide. We have all rode the school bus before, right?
No.
We all have past experience with the school bus. Okay, so here's Dalton down here. Let's say Dalton looks across the aisle and he's talking to this girl.
No chance.
Maybe he has a chance, I don't know.
Sorry.
Would that make a good reference point for Dalton, this girl?
No.
No. Could he even really tell that he's moving if he's just looking at that girl?
No.
No. Because she's moving in the same bus as he's moving. What would make a good reference point for him?
Something outside.
He would then have to look out the window, okay? Maybe there's a tree out there that he's passing. Something stationary, something that's not moving. All right. Okay, a frame of reference. We're going to talk about this for a second. Frame of reference is the way you choose to view motion. It's the way you choose to view motion. It usually includes a reference point, which is a stationary object we just talked about, in order to detect it. So it's a reference frame is the way you choose to view motion. Usually includes a reference point, which is stationary because that's how we can detect motion. So example, like it says here, if the kids on the bus use the other kids as a reference, as a frame of reference, they wouldn't be moving. But if they change their frame of reference to something outside of the bus, like a reference point, like a tree, then from that frame of reference they would be moving. So that's where motion gets a little more complicated. It gets a little more complex than just what we think on the surface. So this chapstick that's sitting on the counter, if you're watching the video, just this chapstick is on the counter. It's just sitting there. I like to ask this question, is it moving?
No.
Yes.
Yes, with the earth.
Well, relative to what?
Huh?
Relative to what?
Good, that should be your question. Relative to what? From what reference point? Now, from the reference point of you, is this chapstick moving?
No.
No. From the reference point of this counter, is the chapstick moving?
No.
No. Now, what if you were outside of somewhere on the earth? Say you were on the sun. Now, you couldn't obviously live on the sun, but
How about the moon?
that's our reference point. Oh, the moon. That's a better one. Say you're on the moon. Is this chapstick moving?
I wouldn't be able to see it. So
Yes.
relative
But
to what?
If we could see
whether you can see it or not, is it moving?
Perhaps.
Yes. Do you guys know how fast so the Earth has a couple of different motions. The Earth is spinning about its axis. Do you guys know how fast we spin?
It's 2 miles per
52
second.
miles an hour.
It's about 900 miles per hour. Okay? We're also orbiting in an orbit around the sun. Does anybody know how fast that orbit is?
365 and a quarter days.
That's a length of time, but what's our speed? Does anybody know how fast it is?
Oh, 5,000 meters per second.
It's about 67,000 miles per hour. So are we moving right
I
now?
was just gonna say per second, so it's kind of space.
That's not even fast.
So are we moving?
Yes.
Yes. So that's just an example of frame of reference. How you choose to view motion is very important because motion is relative, which means you compare it to something else. Okay, I've got this awesome YouTube clip
Oh, sweet.
It is cool. It was made in 1960.
I can tell.
1960. So you're gonna be able. It's black and white, and you'll be able to tell it's really old. But these guys do a great job of explaining how motion can change depending on your frame of reference. They're going to go through a lot of demonstrations and show from a different frame of reference what motion would look like. So pay attention. We're not going to watch the whole thing, but because it's way too long, just for the sake of time. But I'll show you the first 5 minutes or so.
We have time.
Yeah.
We need to get extra legendary like Brandon.
Don't I have like 4 more than you, Brandon? Because
We're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
awkward silence between them.
You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
It's okay. That must be Professor Brown.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things. This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line. As you can see, the electromagnet is mounted on a cart that can move. I'm going to do exactly the same experiment that Dr. Hume did, but this time, while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released. At that point, if it had fallen straight down, because the cart moves on and the time that it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. And this time, I'm going to let you watch the motion through a slow motion camera, which is fixed here. As the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there'll be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more. And this time, I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference point. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent. Dr. Ivy showed you what the motion of...
Okay, so I think we'll stop it there, but they continue on and they do a great job of explaining and showing us just barely that it really does depend on your frame of reference. How you choose to view motion makes a big difference. And so, we'll continue on. Okay, so back to your guided notes. So what is your frame of reference if you're standing on the sidewalk and you see a bus go by? How can you tell that the bus is moving?
You might look at the ground or something.
Well, yeah, the answer says your frame of reference might be the trees or other stationary objects across the street. That's how you could tell that the bus was in motion as it went by. So, a frame of reference. If you were in the bus looking at somebody else in the bus, could you tell you're moving? No. So it really does depend on which frame of reference you choose to view. Okay. This is a very important slide. It's called constant velocity reference frames. So constant velocity reference frames. Frames of reference where you're moving at a constant velocity. They are known as inertial frames of reference. An inertial frame of reference is a frame of reference when there is constant velocity. You have to write that in your guided notes. So an inertial frame of reference is a frame of reference where there is constant velocity. And these frames of reference are a little tricky. So I've got I've got 4 examples here. We're going to go through them and talk about them, each one. So this first inertial frame of reference, an elevator that is moving at a constant velocity of 2 meters per second. Now we've all been in an elevator. When it's moving at constant velocity, can you tell that you're moving? You can't. Now when you get in an elevator, initially you feel that acceleration. We can tell we're moving. And right when you're about to get to the floor you want to get off on, it slows down and we can tell that you're moving then. But in the middle section, where it's moving at constant velocity, could you tell you're moving? No. Okay. That's called an inertial frame of reference. What about traveling in a jet airplane at 600 miles per hour? Constant velocity. You're in a jet. Can you tell you're moving if it's going at constant velocity? No. Can't tell. So again, that's an inertial frame of reference. But there's also others. What about the Earth rotating about its axis? So the Earth spins once every day about its axis. It's going at 1,000 miles per hour. That's fast. How come we can't feel that? It's going at constant velocity. Now, what if the Earth was to accelerate its rotation about its axis? Could we then feel it? Yes. What if it was to slow down or decelerate? Then we would feel it. But it's going at a constant velocity, so we can't feel that. Okay, now there's one more. What about the Earth revolving around the sun? We all know that it takes 365.25 days to get around the sun. That's what 1 year is. How fast are we moving, though? 67,000 miles per hour. We can't feel it because, again, it's constant velocity. So the main point that I want you to understand is right here. You cannot feel motion when you are in an inertial frame of reference. Just like you can't tell if you're moving on an elevator, we can't tell we're moving at a constant velocity around the sun. It's going at a constant velocity. So those frames of reference, they're called inertial frame of references. Okay, one last section on this video. We're going to talk about relative velocity or relative motion. Okay? Relative velocity, you're supposed to write it down in your books. Relative velocity is the velocity of one object relative to another object. So another way of saying that is the velocity of one object compared to another object. That's what relative velocity means. Okay, an example. Car A is traveling at 50 miles per hour, while car B is going in the opposite direction and it's going 60 miles per hour. Now here's the question. If you were in car A, how fast would it seem like car B is going? So you're in car A, how fast would it seem like car B is going? Think about that for a second. We're going to come back to it. You're going 50, one direction. The other car is going 60 miles per hour toward you. How fast would it seem like car B is going?
90?
Think about it. We're going to come back to it.
Not 90, 110.
Okay, we've got an easy way to figure that out. When calculating relative velocities, use the following equation. We are going to use this equation a lot in this chapter. There's a spot in your book to write it down. So take a second and jot that down. Now, I want you guys to get used to saying it a certain way. So when you look at this formula, we're going to say the velocity of car A relative to car B. So it's not VAB. I want you to say it this way. The velocity of A relative to B is equal to the velocity of A minus the velocity of B. How do you say this part again? The velocity of A relative to B is equal to the velocity of A minus velocity of B. Okay, now I'm going to show you how we use this formula to solve this example problem up here. First of all, I always think it's a good idea to draw a picture in physics problems. Okay, so we've got car A here. Car A is moving how fast? 50 miles per hour to the right. Well, it says car B is going in the opposite direction, so let's draw car B. Okay, B is going 60 miles per hour in the opposite direction. Now let's use this formula to figure out the question, which was, if you were in car A, how fast would it seem like car B is going? Okay, now, it does depend on the situation. So let's read this last sentence one more time. You are in car A. So here you are. Okay? How fast would it seem like car B is going? Now, let's look at this part right here. Are we going to have the velocity, are we trying to find the velocity of car A relative to B? Or are we trying to find the velocity of car B relative to A? We're trying to find, we're in car A, so isn't it all relative to A? So we want this one. And so if we write the formula, it's going to be velocity of B minus the velocity of A. So let's see if we can do this. What is the velocity of B, guys? B is right here. It's going 60, but it's to the left. So I'm going to plug in numbers. I'm going to put in a minus 60. Why minus, guys? Because it's going left. And left in physics means negative. Okay? Now this negative sign right here is built in. We don't change that. Minus, what's the velocity of A? 50 to the right, so it's positive 50. Okay, so what is that? It's a minus 110 miles per hour. So if you were in car A, looking at car B, it would look like it's going 110 miles per hour. Now, why a negative sign? It's obviously not going to have a negative speed, but why the negative? Because if you were in this car, which way would it look like car B is going? It would look like it's going to the left, and left in physics is negative. So that's how we use that equation. Hopefully, I've got a few practice problems. We're going to go through them. Hopefully it will make sense as we get through. Okay, practice problem number 15. Okay, it says, consider the moving walkway below. Have you guys seen these moving walkways? They're in airports. Okay, why do they put them in airports? I mean, it's not an escalator because it doesn't go up to the next floor. It stays on the same level. Okay, for a couple reasons. Maybe you have heavy luggage, so you get on here and you just sit there with your luggage and just stand and take a breather, right? But what are they really there for?
Lazy people.
No. That's what some people use them for, is to just sit there. But what are they really there for?
Because they're cool.
Have you guys ever been on them?
Yes.
Yeah. So if it's moving, and then you walk while it's moving, what is your speed relative to the hallway over here? A a lot faster. So even though you're walking, if you look over at a reference point, say this picture on the wall, it kind of looks like you're jogging because you're moving at a lot faster rate than just your normal walk. You've got to add in your velocity that you're walking with the velocity that this walkway is moving. If you've never done it, go to the airport. You gotta get on one of those and try it.
Just go take a flight.
Now, if you start running down this thing, now your running velocity is added to whatever it's moving already, and you're really moving. So it's really put there in the airports for people that want to get somewhere faster. You can get to the other part of the airport a lot faster on that. You're supposed to walk, but you can sit there, I guess. Just take a breather. Okay, let's answer the question. Okay. So if the walkway is moving at 1 meter per second, so this is already going 1 meter per second, and I was to throw a ball at the speed of 3 meters per second to someone who is not on the walkway, what horizontal velocity does the person on the ground measure the ball? Okay, let's draw a picture. You're standing on this walkway that's moving 1 meter per second. Then you throw the ball to somebody over here. Now this person's standing off to the side. Okay? This person's standing next to the wall. If you throw the ball at 3 meters per second, and you're already standing on the walkway that's going 1, how fast is it going to feel like this guy sees that ball moving? Good. This guy is going to experience the ball moving at 4 meters per second. How come? Yeah, you add the two velocities together, you go in the same direction. So 1 plus 3 is 4. I have a story to tell you about this part.
Sweet.
One day I was just outside and I was watching these high school kids drive around in this car. And what they were doing is they had water balloons. And so they would try to find people on the sidewalk, just random people. I don't think they knew them. And they would chuck them at them. So when they saw somebody on the sidewalk, they'd kind of drive closer to the sidewalk. But I don't know if they realized that their velocities are relative, right? So the car's already, say it's going 30 miles per hour. And then the guy grabs a balloon and like leans out the window and hucks it at somebody on the sidewalk. And say he has like a somewhat of a decent arm. Say he throws it 40 miles per hour. That's really just a lob. But if the car's already going 30, how fast would it hit that person? 70 miles per hour. Does that seem a little bit harsh? Doesn't it?
No.
And so it hits that person and basically knocks him down.
Hey, people in MLB get caught in baseball 90 miles per hour.
Yeah, that's true. Okay, but now say, guys, that person on the sidewalk is jogging 5 miles per hour toward the car. Now it's going to hit them at how fast? 75. Anyway, just a little story. All right. The answer was 4 meters per second. We were right. Okay. Guys, I've got practice problems 16 and 17, and then we'll be done with this video in this section. So stay with me. I promise you're going to want to pay attention to this. Okay? Practice problem number 16, it says two cars are headed towards each other. Car A moves at the velocity of 30 miles per hour due east. Car B moves at the velocity of 60 due west. Now we've got two parts, A and B. A says, what is the velocity of car B relative to car A? And then part B says, what is the velocity of car A relative to car B? So it does matter how you define this motion. Okay, so I want to go through this with you slowly. Please pay attention. We're going to use that equation. What's the relative velocity equation again, guys? Let's write it down. Velocity of A relative to B is equal to what? Velocity A minus velocity B. Good job. Okay, we're going to use that to solve this problem. So let's do A first. It says, what is the velocity of car B relative to A? So if you were going to draw yourself into the car, which car are we viewing it from? relative to A. So we are sitting right here in car A. So let's write our equation. The velocity of car, what would we say? B relative to A is equal to the velocity of B minus the velocity of A. Okay, now let's just plug in the numbers. Okay. What's the velocity of car B? 60, but which way is it going?
Negative.
Going left, so it's going to be a negative 60. Now this negative sign right here, we don't change. That's built into the formula, so keep it there. Minus the velocity, what's the velocity of car A? 30, and it's going which way? To the right, so it's going to be positive 30. Okay, so what's a minus 60 minus 30? That's equal to a minus 90 miles per hour. Okay, that's what, whoops. So minus 90 miles per hour. Okay, that's what the answer to part A is. Now, can you really go a minus 90 miles per hour, guys? No. What is the minus sign telling us? That when you're sitting here in this car, which way does it look like car B is going? To the left. And left in physics means negative. So that's why it'd be a negative 90 miles per hour. Okay, now let's answer part B and see if we can see the difference here. It says, what is the velocity of car A relative to car B? Now, which car are you sitting in? We're viewing this motion from car B. How did we know that? It says relative to car B. So we've got to be in car B. All right, now let's write the equation. How would we write it this time? The velocity of A relative to B is equal to what, guys? Good. Velocity A minus velocity B. Now let's plug in our numbers. What's velocity of A? A is 30, and it's going to the right, so it's positive. Good job. 30. Now, can we change this minus sign? No, it's built in. What's the velocity of car B? 60, but it's going left, so it's going to be a negative 60. So that's how you would write it. Minus a minus 60. What's 30 minus a minus 60?
It's positive. It's a plus.
It's 30 plus 60. So what is that? 90 miles per hour.
Let's do 17 on.
Okay, now, before we're done, that's the answer, but before we're done, if you're this guy in car B, it looks like car A is going 90, but why is it positive?
Because it's going to the right.
Because it looks like car A is going to the right. So again, that sign just tells us direction. Okay, good job. And so we did get the answers right. Okay, last practice problem. It's number 17. It says car A is moving due east with a speed of 30 miles per hour, and car B is moving due north at the speed of 30 miles per hour. Let's draw a picture. Okay? Car A is going which way? East. Which way is east, guys?
Right.
To the right. At how fast? 30. Okay, so it's going 30. And car B, this was car A, car B is going north at a speed of 30 miles per hour. Okay, so at the same time car B is going north. North is straight up, isn't it, guys?
Yeah.
At 30 miles per hour. Okay, let's answer the questions. A little bit different this time. It says, what is the velocity of car A relative to car B? Let's say that they started at the same spot. Okay, so we've got this sort of situation going on. A is going 30 this way, and B started at the same spot and is going north. So they're both going 30. Now it says, what is the velocity of car A relative to car B? So where are we, guys? Which car are we in? We're in car B. So we're up here in this car. There's you. You're looking back at car A, wanting to know how fast it's going. How do we solve this?
You have to use the fact thing.
Good. What's it called? Pythagorean theorem. Okay. If we find the vector that's along this line, how would we do that? This is a right triangle. Good. Pythagorean theorem says a squared plus b squared is equal to c squared. So, what is a? 30. We're going to call it doesn't matter. This leg of the triangle is a. 30 squared plus b is also 30 squared is equal to c squared. So grab a calculator. What's 30 squared, guys?
42.4.
Good. 900 plus another 900 is equal to c squared. So that's simplifies to 1800 is equal to c squared. How do I get rid of the square, guys? Square root. If I square root that side, do I have to square root this side as well? Yes. What is the square root of 1800? So c is equal to 42.43. And we're measuring in what? Miles per hour. Okay, now let's think about the sign, or let's think about the direction. You're sitting here, it looks like car A is going which way? To the right, but it also looks like it's going down. So a little bit complicated. We'll say it's a positive 42.43 meters per second. But let's give it a direction so that we don't have to worry about the sign. Which way would it look like it's going? Well, it obviously looks like it's going east, but also which way? Southeast. So, okay, let's think about it. You're in this car.
Oh, we're in B?
Yeah.
Oh.
So doesn't it look like it's obviously going to the east? We know that. But wouldn't it look like it's going to the south if you're in car B?
I thought we were in A.
Yeah. So instead of putting the sign here, guys, instead of putting a sign, if you put direction, does that mean the same thing? Sure. Okay, now let's do B. What is the velocity of car B relative to car A? Now which car are we in? Relative to car A. So now we're not in B anymore. We're sitting in this car. Would the speed change? No, the velocity is still going to be the same, 42.43 miles per hour. But now let's put a direction on it. Which way would it look like car B is going? Yeah, it's going to look like it's going to go to the west and to the north. So we'll talk about later in physics, later on in the course, how we can find the angle here and the angle here. Okay, there's a way to do that, but we haven't really got to that point yet. Okay, hopefully that makes sense. And so, yeah, we got it right. 42.4. They just rounded it to 1 decimal place. All right, guys, we've learned enough to do a worksheet in the student workbook. So please open your books and complete the following worksheet. It's called Frames of Reference Worksheet. Frames of Reference Worksheet. Okay, and hopefully this video helps you complete that.